Welcome to This Explainer. Today, we're going on a bit of a journey. We're diving past that frustrating surface layer of the AI chatbots we wrestle with every single day, and we're going straight down into the mathematical core of machine intelligence. Have you ever felt like you have to play mind reader just to get a helpful answer from an AI? Or maybe you're wondering how these machines are eventually going to collaborate to do real, rigorous science. Well, if so, you're absolutely in the right place.
So let's start with a shared frustration, right? The classic linear prompt box. When we're talking to a frontier AI model right now, we're basically trapped. It's this endless cycle of prompt, response, correction, response. But think about it. That is not how the human mind actually develops complex ideas. We branch out. We reconsider our assumptions. We ask, what if? Expecting us to just magically construct the absolute perfect prompt right out of the gate, honestly, it's fundamentally misplaced.
Here is our roadmap for today. We're going to quickly hit on the limits of the prompt box, explore something called the semantic inquiry workspace, plunge into the formal math of machine knowledge, map across scientific domains, review a concrete pilot, and then wrap up with the future of AI inquiry. Let's get into it.
Section 1. Beyond the prompt box. Let's take a look at the friction of modern chat interfaces.
The crucial thing to remember here is that human language evolved for us to communicate intention, emotion, and shared social meaning. It's incredibly flexible, mostly because it relies heavily on unstated context and, well, human ambiguity. But that exact flexibility makes it a highly inefficient and unreliable medium for AI agents trying to exchange advanced scientific reasoning. When agents are just passing giant paragraphs back and forth, they have to constantly guess, like, is this a hypothesis? Is it a proven fact? Maybe an analogy or a simulation? You see, natural language can effortlessly hide category errors, and in science, that is a really dangerous game.
Moving on to Section 2, the semantic inquiry workspace. This is the human-facing solution proposed in the research.
Now, what's really fascinating here is how the interface reflects the emerging structure of your inquiry before you even hit send on a prompt. Imagine this. As you're writing, a compact, expandable semantic tree is building right alongside your text. Suddenly, your concepts, your hidden assumptions, and your unresolved issues become these durable, inspectable objects. It's not just auto-completing your sentences anymore, it's literally making the entire structure of your thought explicit.
Contrast the buried, lost branches of a normal chat transcript with this highly navigable semantic surface. In a typical AI chat, your alternative ideas just get totally lost in the scroll, right? But here, you can actually isolate reflection nodes. You can explore these what-if counterfactuals without ever losing your primary line of thought. A suggested little nugget of knowledge becomes an inspectable object. You can expand a branch, test out an assumption, and then just decide later if it even belongs in your main prompt. Nothing gets tossed away just because it wasn't the immediate answer.
And that brings us to an absolutely crucial safeguard, the provenance inspector. This system surfaces issues like model anchoring. That's basically the risk that the AI's suggested structure is secretly biasing your own framing of a problem. This brilliantly proves a major point. Just because a model infers that a concept is relevant, that does not give it automatic authorization to become active context in your prompt. You get to see exactly where an idea came from, whether you authored it, whether it was pulled from a source, or if it's just a wild AI inference.
You have total agency here. You can literally drag a selected node right into the prompt. And check this out. You aren't just pasting text. You can attach a specific label, a concise definition, select relationships, or even bring in an entire bounded subtree. This matters immensely because, as we know, a concept carries dependencies and contradictions. You, the user, explicitly authorize exactly what enters the model's context.
All right, Section 3, Machine-to-Machine Knowledge. Let's dive under the hood and look at the mathematical backbone.
So beneath all of our messy, beautiful human language, AI agents desperately need a formal mathematical backbone. Scientific domains, think biology, physics, or medicine, can actually compile into these precise H-tuple models. By strictly mapping out things like entities, permitted relationships, laws, and evidence requirements, the system essentially throws up a massive firewall against category errors. An AI simply cannot accidentally treat, say, a mathematical simulation as an observed clinical fact. Why? Because the formal structure literally will not allow it.
Instead of generating paragraphs of prose that another AI then has to interpret, agents are going to exchange these canonical scientific representational objects, or SROs. Imagine one AI sending a data packet that explicitly lists the domains, the epistemic class, like, hey, this is just a candidate hypothesis, the exact assumptions, and the mathematical model.
This drastically reduces token overhead, for one, but more importantly, it totally prevents the loss of semantic meaning during the exchange. There's zero guessing involved here. The scientific assertion is machine native and perfectly bounded.
But, look, we all know uncontrolled AI growth is a massive risk. If models are just out there endlessly inventing new concepts, we get semantic drift. It gets messy fast. That is exactly why every single new ontology object must survive this really strict, multi-step governance lifecycle. It starts out as a mere candidate. From there, it has to be attributed, inspected, and aggressively challenged. Only after it passes experimental support and domain expert review can it be canonically activated. Silent, sneaky promotion of ideas is strictly forbidden.
This actually brings us to the guiding philosophy for this entire architecture. And it's a great quote. Intelligence proposes, authority and evidence determine what becomes canonical. An AI can spot a cool pattern and suggest a brilliant new category or model compilation, sure, but it cannot independently certify that as truth. The system completely separates the intelligence required to generate an idea from the authority required to make it an actual scientific fact. Okay, Section 4, Mapping Across Domains. This is where finding cross-domain relations gets truly fascinating. Mapping structures across domains isn't just about creating attractive metaphors. Like just saying biology is like a computer network isn't nearly enough. It's a rigorous, three-stage discipline. It starts with heuristic noticing, a wild hypothesis. Then it moves into formal mapping construction, where the system strictly bounds what structures are actually preserved and which ones fail. And finally, it demands scientific validation. We're talking actual falsification here via simulation or real-world experiment.
So the absolutely crucial point to take away from this is that the math itself does not constitute a scientific discovery. Having that mathematical backbone just makes the AI's analogy precise enough for us to actually test and falsify it. The formal map tells you exactly what assumptions were injected and precisely where the mapping falls apart. It cleanly separates a tentative hypothesis from an established result.
Moving on to Section 5, the minimal pilot. Let's see how we can test the boundaries of this system.
Let's put this whole thing to the test. Imagine using the semantic inquiry workspace to pit an AI trained purely in biology against an AI trained in distributed IT systems. We force these two completely distinct mathematical ontologies to tackle one exact question. Could a biological repair mechanism suggest a new approach to computer fault recovery? It's a wild concept.
And the results are just fascinating. The AI formally maps the biological concept of local damage detection to the IT concept of fault detection. It maps tissue repair to state restoration. But look closely at that bottom row. It maps autoimmune response to false positive defensive escalation and explicitly flags it as a candidate failure mode. This is massive, honestly. It proves the system isn't just a yes machine churning out pretty analogies. It actively finds exactly where the cross-domain map breaks down.
Finally, Section 6, the future of AI inquiry.
The authors here deliberately limit their architecture to these 5 bounded, highly testable claims. They state plainly that compilation isn't truth and that governance is absolutely required to prevent that messy semantic drift we talked about. But most importantly, the value of this system must be demonstrated through rigorous, comparative experiments. Honestly, this deliberately modest approach is actually an open invitation for aggressive, adversarial testing from both the scientific and the open-source communities.
If you take away just one golden rule from this explainer today, let it be this: relevance is not authorization. Just because an AI retrieves a contextually relevant fact or generates a super insightful branch, you maintain the ultimate authority on what actually enters your inquiry. We are finally moving past those transient, opaque chat logs into a totally new era of durable, reconstructible, and governable knowledge.
I want to end on a bit of a provocative thought to leave you questioning your own daily AI habits. As we transition from these simple autocomplete chatbots into an era of governed, formal scientific collaborators, how will you architect your own inquiry? Are you going to keep settling for a linear prompt box, or will you start demanding the tools to inspect, branch, and strictly govern the knowledge you create? Think about it. Thank you so much for exploring this fascinating material with me today, and as always, keep questioning the interface.